Welcome to the afternoon session. Just two things to say before we start. Tomorrow we haven't scheduled any official seminars. The idea is tomorrow should be a day free for informal discussion. So we encourage you to make use of that, of course. Next week, Tom Bridges will be the main organizer, scheduling talks and so on. So if you have any questions about next week, then talk to him. Or if you want to give a talk next week and you haven't been scheduled yet, please talk to Tom. Of course, you can talk to us as well, but we'll just forward your query to Tom. So, okay. And now we're going to return to the subject which started yesterday with the talk of Guido Schneider about justification of model equations in general and the nonlinear Schrödinger equation in particular. Our next speaker is Nathan Totz from Duke University, and he, like Guido, is also going to talk about justifying the nonlinear Schrödinger equation as a modulation equation for waterways. Please.
Well, thank you very much. Thank you to the organizers for inviting me here. This is lovely to be here. Yeah, just as Mark said, we're going to be talking about justifying the nonlinear Schrödinger equation as a model equation to a certain kind of nonlinear wave equation. In this case, I'm going to focus on the waterway problem. And whereas Guido's talked about lots of different situations and variations, such as including the finite depth and the effects of surface tension, I'm going to focus very intensely on a very specific situation, sort of an ideal situation, one that has infinite depth and no surface tension. And I'd like to talk about the 2D problem in some detail, where it's easier to write down the calculations and things. And after that, I'd like to talk a little bit about the same problem in 3D. And I won't go into as much detail, but I'll tell you about some of the major differences and difficulties there. So to start off with the 2D situation, here's a picture of the kind of thing I'm talking about. This is a wave tank where they're exciting a modulated plane wave, and they were able to engineer a relatively large amplitude wave to appear some ways down the tank. And the way they were able to do this was with predictions given by this nonlinear Schrödinger equation. And my talk is about this, about saying that somehow you have this approximate calculation that says that the nonlinear Schrödinger equation should govern the envelopes of things like this, and to justify that mathematically is what I'm going to talk about today. I'll apologize in advance for all the experts in the audience who already know about many of the standard techniques I'm going to be talking about in a little bit more detail, as well as for stepping on Guido's toes a little bit, since a lot of that will also be repeated. And case in point here, I'm going to tell you the governing equations for water I'm going to be using. The incompressible rotational 2D Euler equations, which all of you have seen innumerable times at this point. So here they are. The only thing I'll mention at this point specific to us is that I'm dealing with an infinite depth case again, and I'm also dealing with the case of no surface tension. And what we very much like to do is to reduce to the problem on the surface, which we're allowed to do in the rotational case, which is the case that we're in right now. And this formulation, which is the formulation due to Sijué, is the one I'm going to be using, and it's not as familiar as some of the other formulations we've been using, so I'd like to go through that. So the first thing that you do is recognize that, well, this is a potential fluid, and so it's suffice to determine the motion of the interface. So you immediately parameterize this in Lagrangian coordinates and write down the evolution equation. The acceleration term merely becomes a second time derivative. Here, my gravity has been normalized, and I'm using complex variables to do everything in 2D, and so that's why we have this plus I over here. And the pressure term has become this term here, and the reason I'm allowed to write this is because I've assumed that the pressure is 0 in the interface. It's a level curve. Therefore, gradient is going to be normal, and you can write it as multiplication by I of the tangent vector, z alpha. It turns out the way we have things set up, that's going to be pointing outward. And this is only at the scalar multiples. The scalar multiple that you pick is this A here, and the fact that this A is always positive is something that Sijué showed in some of her work. It shows that the Rayleigh-Taylor instability doesn't occur in this problem, so we don't have to worry so much about that. To say that this is, again, a sort of a potential flow, when you write this on the surface, you get this condition using this Hilbert transform associated to the interface curve Z. So we have two now equations here. These are the equations I'd like to use. So ideally, what you'd like to do is you'd like to say, okay, well, I'd like to look at a small wave packet. And you have to choose the scalings, like Guido said yesterday, in such a way that you end up getting interesting behavior out of equations involved. So that's the meaning behind using these particular scalings in the amplitude and the slow variables. And you can do this sort of geometric optics calculation. And what you expect is that this amplitude will sort of translate at this group velocity. And on very, very slow time scales, epsilon to -2 time scales, very long, it will evolve according to this cubic nonlinear Schrödinger equation, which I haven't written down yet because we'll see it later. And this is fine, but this is still sort of a formal calculation. You're assuming that you can make this Taylor expansion and that everything will converge. And, this is what justifies you using all these solvability conditions and things. You very much have to justify this. And, well, what you'd like to show to justify this is, first of all, that you can indeed, in some appropriate function space, find an approximate solution such that when you plug it into the earlier equations, these leftover terms that you get after truncation are sufficiently small. Somehow, lid low of epsilon cubed ends up being sort of the most you can get away with in some sense. Of course, you'd like to show that the waterway problem with that wave packet like initial data in fact exists for the appropriate amount of time where there's really nothing to do. And then you'd like to show that this true and approximate solution stays sufficiently close. And you don't want the remainder to be as big as either the things that you're comparing, of course, so you want it to be a little low of epsilon in the appropriate function space. And that kind of depends on the scaling of epsilon and whatever space you're using. It may make it different. But this is what you'd like to say as far as justification. So I use rigorous justification. I guess David Mons now calls this fully justified in his water wave book, I think. So that's I need the same thing as this. Okay, so I'll tell you what work I know of about this. So as far as formal derivation with Zakharov, derived down less in '68, and using this multi-scale method, the earliest one I could find was this paper in '72 of Hashimoto and Ono, and they did this in the Eulerian framework instead of the Lagrangian framework. And there may be others, but these were sort of my two go-to references. As far as people trying to complete the steps that I listed on the last slide, there was this nice paper of Craig Sulem and Sulem in '92, and essentially what they did is they took this 2D waterway problem with finite depth, and they said, oh well, we will calculate the residual. We will be very careful about all the singular integrals and things that appear. Well, they think about Dirichlet-Neumann maps, but potato, potato. And they got control over the residual, which is sort of the consistency part of the proof. And then I guess a little bit later, Craig Sulem and Chance in the later '90s, they did the same thing in 3D, but instead of having control over the residual in L2, they did this in LP for P bigger than 2. And that'll be a little important for my purposes later, but this is the kind of thing that you want anyway. And then very recently, as we heard before in Guido's talk, Wolf Patrick Duhl and Guido Schneider and Gene Wayne, they have a recent preprint that does the full justification in the 2D finite depth case, whereas mine is the 2D infinite depth case. And as he mentioned, there are some big differences in the methods that we use from one to the other. So what's the problem here? I mean, ultimately what the problem comes down to is wave packets are just pretty big when it comes to scaling. So if you look at what these things look like in L2, oh, this should not be, oh, I see, yeah. So the trouble with this is wave packets in L2, when you write out the L2 norm of this with all the epsilons and such, and you crank it out, getting the wave packets look like the square root of epsilon size. And in 3D, in fact, the scaling is kind of critical, and you get, it's 0.1. It's not even small in that sense, technically. And so when you try to just use standard existence results for water waves, you don't get nearly as long of a existence time as you should. And the trouble with that is, if you try to write down what's going on, at best, the only thing that you can really say about this is, well, you've got this initial modulation, and the best you can say is that it's traveling like a traveling wave. It's essentially you just take the initial data and it translates, and you can't justify anything more than that. Sometimes you don't even get that. Sometimes it just acts like a plain old plane wave. So this is no good. So how do you fix it? Well, here we're dealing with more or less small data. And so if you have small data and you've got a big nonlinear wave equation, of course you like to have your degree of your nonlinears to be very big, because then they will be very small and easier to handle. And it turns out that the kind of threshold that we want for our purposes here are cubic nonlinearities. Those somehow are the best. We'll see those a little bit later. And lucky for me, certainly, CJ has a formulation for the water wave equation where you can change variables with this very amazing and at the same time mysterious change of variables that depends on the unknown interface and the Hilbert transform. And it converts the Lagrangian variables into these new variables. It satisfies the equation of this form. So we're thinking of this quantity, this sort of a projection of the perturbation of the interface from rest. And we're thinking of that as the unknown. And somehow when you apply the water wave operator to this, you end up getting something that is just a cubic in higher order. And this is really great because this is somehow exactly what we need. So the idea then is, well, okay, so we change variables in this new coordinate system. We do the justification there, and then we try to change variables back. And then hopefully that'll tell us something about the original Lagrangian situation. So we go and do it. So you expand in a series in epsilon like this. And corresponding to this, you can of course also expand the kernel of the Hilbert transform formally and justify all that and get an expansion for the Hilbert transform as well. And the way that this is done is you replace each of these dependencies on these slow variables with other variables, multi-scales, what they call it, like this. This is one of these parts where I have to apologize for going over multi-scale calculation again in case you're very familiar with this. And when you do this, you have to interpret everything in terms of these new multi-scale variables. And it's pretty clear what to do for space and time. You just use the chain rule, essentially. This is what it should be. And the question is, how do you deal with the action of this Hilbert transform on multi-scale functions? So like I said, you can expand this. And as is typically the case, you get so correctors of the Hilbert transform depend only on basically more and more complicated commutators of this flat Hilbert transform, just for the rest interface with the correctors of the unknown, and that's perfectly fine. So now we've reduced the problem understanding the flat Hilbert transform. And the other clue that we have is we're going to only be dealing with functions that are wave packets, so they're concentrated about a fixed wave number k. And so you do a little Fourier analysis, and what we end up doing to interpret this is as follows. So if you have a wave packet with a non-zero wave number, then you just use the symbol of the Hilbert transform. And it turns out that if you write that down, you get as small an error as you want for a smooth f. And if you have zero wave packet, it doesn't work so much anymore. But if you look at what the flat Hilbert transform is, it's dilation invariant. So the way you should interpret one of these functions, slow variables alone being acted upon by the Hilbert transform, is just the Hilbert transform of the function as a function of slow variables. So you just keep that in the calculation then.
How big is m?
One of the features of these calculations is that you're going to eventually have these leftover residual terms. They're going to depend on a whole lot of derivatives of a. And the m here depends on the smoothness of this f that you have here. So we're going to eventually assume like 15 derivatives above, above the Sobolev norm s that we'd like to control the remainders in. So we can make m as small as you want, provided that f is as smooth as you want, which it is. Yeah, I left it like that because we're going to, depending on which problem I'm talking about, we're going to go farther into the calculation. Okay. Okay, so here's roughly how the multi-scale calculation goes. So at the top level, you're just dealing with the wave packet part of this, and you derive the dispersion relation as you should. And somehow, because we have a wave packet that's concentrated on positive frequencies, this projection holds automatically. At the next level, you get this this sort of solvability condition. Here, the idea is kind of like in ODEs, where if this right-hand side is not equal to 0, you would get secular growth, and over the time scales we're interested in, this would not be an asymptotic series anymore. And so, this formally speaking, you say, okay, well then this right-hand side must therefore be 0, and that's what gives you propagation at group velocity. And then this allows you to rewrite your variables as a function of one space variable x and a big, very slow time variable t. For the second equation, I just want to really quickly mention that when you write it down, it's actually only determined up to the kernel of this projection here. And so that is slightly worrying because you'd like, of course, to have a unique answer. And it turns out that if you include something that's not 0 in the kernel at the next level of the calculation, you get secular growth. So this is just a comment I put in to assure you that the correctors are uniquely determined, which is a good thing. And you do a similar thing for the next level. You take all the epsilon q terms. The same kind of thing happens, only this time you get the NLS equation is enforced. So there it is. And now we're in deep water, and this looks like a minus, but this actually, this second derivative of omega with respect to k, that's actually a negative number. So this is really focusing like it's supposed to be. And that's really the interesting part of the calculation. You can develop the correctors past there, and it's not particularly interesting, but you can do it. Okay, so that's consistency, and that's sort of step one. And steps 2 and 3 where you need the existence of the waterway problem, and you need these remainder bounds. So to get equations for the remainder, what else can you do besides take the real and approximate quantities and subtract them and show that they're small? That's certainly what I would do and what I did do. And it turns out that the structure of Sejoy's formulation is such that it's very convenient to take the projection using this Hilbert transform associated to the interface. That ends up making many technical things work out. And you also need control of the time derivatives to close everything. And it turns out that I'm not even going to write that down because you have to very carefully choose this in order for the energy estimates to work out. The part I do want to show you, though, because it's actually something that you can work out, is you got these remainders, and you have this parameter epsilon that determines how small things are. And the question is, well, how small should we expect it given the size of our residual and our nonlinearities and things? So I'm going to jump right to a toy equation instead of writing down the water wave equations. And so this is sort of here we have a cubic nonlinearity, and there's the linearized water wave operator on the left-hand side there. And the approximate equation, remember, is we found a approximate solution W with a twiddle over it that satisfies the equations up to very, very small remainder terms, and I'm going to leave the size of those terms open and call it beta. So you subtract them, and you get an equation for R, the difference. And you proceed to do an energy estimate. So here would be the natural energy for this thing. I'm forgetting, for the purposes of the toy discussion about regularity, I mean, this is something you have to be very careful about in the real equation, but let's just pretend that we can do this. And the kind of numerology that you get here is this sort of thing. And in reality, it's a lot more complicated. There are many more terms, but in essence, they fall into one of these two terms here. So immediately you go to Gronwall. Gronwall now gives you the following bound, like this. So on the one hand, the time variable appears with a epsilon squared in front of it. That's because we had the cubic. And then we have some epsilons in front that tell you how small the energy could be, which is how small the remainder is. So the upshot is this. So this sort of confirms that the power of the nonlinearity determines how long you can expect your remainder bound to hold, which is why we need cubic, because we need at least that long. And it turns out you can, from the size of the residual, you can work out how big the remainder is supposed to be. So the more you develop your approximate solution, the smaller you can make your remainder. That's kind of the two things we put into this calculation, I guess. Okay, so now I'm going to completely gloss over, actually doing this toy calculation in the real water wave equation problem. It's quite a few details, and be very careful, but that's the basic idea. So supposing we have these remainder bounds, you can work out the last step, which is the existence of the water wave problems, in a very nice way. And the way you do it is you say, well, okay, so I've got my model equation, my LS, and that's going to exist for so long. And in fact, in our situation, LS is globally well posed because it's completely integrable, so you can just solve it as long as you like. Then your approximate solution makes sense on that same interval. And what this means now is for the 2D case, which is what I was talking about there, you've got these a priori remainder bounds on the same length of time. So what that means is you can control the water wave solution for that amount of time just by writing it as approximate plus remainder. So this is like a priori bound. Yeah.
You started out talking about some time, but then you said because NLS is integrable, I have infinite time. Now when you're talking about that time, are you meaning infinite time, or are you meaning the one you started with?
No, fix a t. And in fact, you have to fix a specific t. So in other words, you got so this is not going to be true for all time. You have to fix then this is a good point. You have to fix a specific t, and constants in the meantime in the problem are going to depend on that t. So you have to choose epsilon smaller and smaller to make it valid for longer and longer.
Excuse me, is t always less than epsilon 1 over epsilon squared?
T is just sort of like the constant comes up in the NLS. So where's my pointer? So you say that. Suppose NLS is exists here, right? then just by the scaling, plugging it into the approximate solutions, the approximation exists on this time scale. So t is independent of epsilon. But somehow, if you want t to
Then
get...
it's not less than 1.
No, t, anything. Yeah. But in order to get justification on whatever that interval is, you might have to take epsilon smaller and smaller as t gets bigger and bigger.
But he's just saying suppose.
Yeah,
So
just...
he's not saying anything yet.
Do you mean suppose there exists a t bigger than 0, such that b exists on...
Oh, I see. Yeah. So this for any is what's throwing people off here. Yeah, it shouldn't be for any. So just suppose, yeah, sorry about this. Yeah, so I guess we should really say suppose there exists a t bigger than 0 such that NLS has a solution on 0 to t, then all the rest of the stuff. Yeah. Okay, but anyway, so the point of this is somehow you've got the approximate solution, which is bounded more or less by hypothesis in NLS, and you've got these remainder bounds, which bounds the water wave solutions. And if you have these a priori bounds on the water wave solutions, you can continue them for as long as the approximate solution exists. So somehow existence of the water wave problem just sort of follows automatically from the first two steps, in some sense. Okay, and here's the theorem. And so the 2D work was my thesis work with Sijue. And here it is. We need 6 derivatives. And suppose you've got a very, very smooth initial data for NLS. And suppose you solve it out to this time big T. Right? Okay, then you can find a small epsilon, which also depends on that big T. And there turns out to be an open set of prepared initial data that the water wave equations is compatible with, such that this initial data is very, very close to the initial wave packet. And then you get that this quantity, which is just the difference, the error, it does not exceed this epsilon to the 3/2, which is strictly less than epsilon, which is what we want. Okay, so this is our theorem 1. This is saying that this justification works in these new coordinates. But of course, now we want to go back to the old coordinates. We have these Lagrangian coordinates. So you can just change variables and see what happens. Well, I mean, on the one hand, velocity and acceleration works out pretty well. Anytime the change of variable shows up by the slow variables, of course, you can just use the mean value theorem and throw it into the remainder. That's not a big deal. This change of variables does show up in the phase up here, though. You can't really get rid of that. And if you look at what the change of variables looks like, you can use your asymptotic information to figure out what this is to leading order. And it looks like this. And this poses a little bit of a problem for controlling the space derivative. And the reason is because when you use a chain rule and write out after changing variables, you get that the real part of the perturbation looks like this is sort of the wave packet you expect to get out here. And here's our remainder that's nice and small, but then you also get this k alpha minus 1. And this is a real problem, and the reason is because even though we sort of know what this is to leading order, the remainder here is epsilon to the 1/2, which is the same size as this main part. So unfortunately, that means that for the real part of the spatial derivative, we don't have a good justification. And the way to get around this is you instead go to Eulerian coordinates. The reason we expect this to work is that, well, okay, so we have in these mysterious transformed coordinates a justification, but this is still a parameterization of the interface, so why not just jump right to Eulerian coordinates, as though you have a graph. And you can do this. The only thing that we would need is we would need to be able to control the very lowest derivative in order to make sense of y composed with x inverse, if you like. And unfortunately, the energies we have control at lowest a half-space derivative. So we don't actually have that control at this point. And in order to get it, you have to actually go to the velocity potential and use other equations of Sijue. And luckily, you can take the following quantity. This is sort of the familiar trace of the velocity potential on the interface, and then you take this holomorphic part again, which you always do in this situation. And it turns out that this will satisfy a similar sort of equation with a cubic nonlinearity here. So you can basically just do the same thing that I did over again, only for this lowest derivatives. And this all works out just as you would expect, and you get the same sort of remainders. The only thing is that when you try to control the initial energy, there's a term that requires you to control this kind of funny function of the velocity potential. And the way that you could think of this, I guess, individually, if you write out what these are in the interface, and you use the divergence theorem, essentially. What this really is doing is this is comparing the L2 norms of the entire velocity fields in the bulk of the fluid. And because those are defined on different domains, we can't necessarily write down that difference literally, and that's what this quantity is supposed to represent. Somehow you need this extra condition on the velocity fields. And then you get this theorem. So now you got an initial graph, and you have the Eulerian velocities and accelerations. And so if you have this initial data, which is less than CF on the 3/2, which by last theorem you always do, essentially. And suppose you have this condition on there's this funny condition on the velocity potential, which is really comparing the velocity fields. Then you have a remainder bound, and solutions exist. Okay, and I believe that is all I want to say about the 2D. So if there are any questions about that, then I'll move on to the 3D part of the talk. Yeah.
I'm just having a question about this transformation where you remove the second order terms. Is it equivalent to removing second harmonics in your expansion?
It is not literally a normal form transformation. So normal form transformation would be, you just take the unknown and you perturb by some bilinear thing.
Yeah.
And if you try to do this, you get something that isn't invertible, essentially. Causes problems. If you do right here.
I'm just thinking of Sakharov did something similar where we remove second order terms.
No, it's not the same.
It's not this, yeah, not quite.
It's not the same. Because after this transformation goes in the velocity level also, then you in the zero frequency, because this is not periodic case. Zarov is periodic case. So non-periodic case, you will have a small divisor at c equals 0. So the change of coordinates removes that.
Yeah.
So there's extra thing. There's a change of coordinates. We're not using. You see, in the Lagrangian or Eulerian coordinates, you still have quadratic nonlinearity. Only when you use this particular coordinates, you don't see the quadratic.
Yeah, but my guess would be that you
No,
remove second harmonics.
No, it's not. It's not. Actually, it's not the second one.
Oh, but yours proposed the transform which you returns for periodic waves.
Yes, it also the formulation works
in
in any sense.
2006, I think. I think it was in 2006.
2006 what?
We proposed this transform which give quadratic terms.
Who proposed?
Yours? No, yours proposed.
Your proposal.
Yes.
Yours.
No, it's not the same. It's not.
It is
Because
not the same?
the transformation is fully nonlinear. It's not bilinear. This is fully nonlinear.
Yes, for fully nonlinear.
Yeah, but the transformation itself is fully nonlinear. People usually do a bilinear one in the velocity potential level, you can do it, but in the velocity level, you cannot. So this is why we can. There's a change of coordinates because the normal form usually they take the ODE idea, they don't think about the spatial. So we have to do something else. I show you later.
There'll be some normal forms later in the talk too when I do 3D. So. Okay, anyhow. So I'll go on, yes.
It seemed like you gave a historical description of what you have done.
Mm-hmm.
You started out with Lagrangian coordinates, and then that got you far enough along, and then you switched to Eulerian coordinates. If you went back and did it all, do you need both coordinate systems?
No, actually. So I think knowing what I know now from the 3D work, I think you can develop the approximate solution farther to where you can actually justify the real part.
In which coordinate?
Lagrangian. Yeah. And Eulerian. Why not? Okay, any questions? Okay. So here's a 3D wave packet. So whereas before I, assumed it was very much plane wave that didn't vary in the horizontal direction, here it's going to be a plane wave that gets allowed to die out in all spatial directions. And the way that I'm going to write this down is using the following ansatz here. I'm going to have it just propagating in the x direction without loss of generality. And you can do all the same calculations. Lots of people have done this before. And in infinite depth, what you end up getting is this sort of this hyperbolic NLS equation, which is a little bit different now than what you got before. So this is sort of this is what you get for Davy-Stewart's and elliptic hyperbolic as you take the depth to deep water. And just as a side note, I found this out while I was reading the literature of this, which is that the global existence for this equation for large data still isn't known. They only have local existence for this, which is very, very much in contrast to the 1D NLS equation where you have this complete integrability and things are great. That being said, that's okay. So wherever this exists, then on that time scale, I can get a justification. So, but it's interesting to note anyway. Okay, so first, I'll tell you about good aspects of this. Well, CJ has a formulation that's analogous to what you did in 2D in the 3D problem. Now, in order to write down the change of variables that we had before, remember, it depended on the Hilbert transform, and so now you have to say, well, what should we take in the 3D problem that corresponds to the Hilbert transform? So we need a generalization of complex analysis, and it turns out such a thing exists. It's called Clifford analysis, and if you've never heard of it before, it's really, really quite beautiful stuff. I'm only going to be using essentially the Clifford analysis corresponding to the algebra of quaternions, which is sort of the appropriate one that we have in this case. But you can use all kinds of algebras in other situations. And it turns out that there's a variant of the Hilbert transform, or generalization of the Hilbert transform, using this. Now, this is you pay for this, of course, by these are Hamilton quaternions, so that means they're non-commutative. So all the calculations are much more delicate, I guess you'd say. Another nice thing about 3D is that you have, just due to sort of the Sobel of embedding numerology, you get control over the L infinity norm. And what this means is that if you wanted to justify the Eulerian coordinates, remember we needed control over that lower derivative, and here somehow in L infinity we had it. So we don't need to do anything with the velocity potential here at all. It's just 3D is just justify Lagrangian coordinates and then we're done. So there's some bad parts, which is that whereas in 2D, this nice change of variables literally eliminated all the quadratic terms. Here, they aren't all quite eliminated. There are a couple that are left over. But they always appear with a very nice structure, this sort of Maxwell null form term structure. It's called various things in various places. But the point is, this has got a nice structure that you can use in various ways. And so when CJ was using these equations to prove global existence for the water wave problem, it turns out that you can more or less treat these terms as cubic when you measure them under the invariant vector fields of the water wave problem. So this is somehow how she got rid of it there. The trouble with wave packets is, of course, I'm assuming that nothing disperses, so we shouldn't expect that would work. In fact, you try to measure these things in the same way, they become far too large in epsilon to work, so you have to do something else. And there's more, unfortunately. So when you try to do the approximate solution side of this, and you work out what is the L2 norm of the residual that you would prefer to stop at, it ends up being of size epsilon cubed, which is unfortunately just a little bit too big to get away with what you want. It turns out that the remainder then is of size epsilon exactly, and that doesn't give you a justification. It says the remainder is the same size as either thing that you're comparing. And if you trace through the argument following through in 2D, it actually is a lot worse than that. And the reason is because when you try to work out the change of variables, you don't have enough control to actually show that it's invertible. It's no longer a perturbation of the identity anymore. But that's a big problem. So the solution to all these things is, of course, to get the remainder to be smaller so that you can get finer control. And the way you do that is just by developing the approximate solution longer. And this took a really, really long time because you've got these quaternion value calculations that you have to do very carefully, and it's a lot of work. But you can eventually do it. And the payoff for it is your remainder is now of size epsilon squared, which is much smaller than you needed to get the job done. There's a little bit of a price you pay for this, though, which is that when you look at the formulas for the correctors farther out, the ones that you need to get all this done, you end up getting terms that look like solid derivative to the -1 f times g. And that's not necessarily an L2, unfortunately. So I had to put extra conditions on A in order to make that work out. What I ended up requiring instead of something like a mean zero condition, which I don't want to deal with, is just that you require that A decays like some algebraic power. It can be anything you want. So just in case, I don't think that anybody expects solitons here, but just in case there was one, I decided to write it like this. The equations are well posed here and everything, so that's okay. So this is where a little bit of algebraic decay is coming in. And I guess this is a substantiation of one of your claims from before, saying that you sort of expect these approximations to hold if you allow a lot of algebraic decay. So here I'm using a little of that, I guess. So this doesn't solve the problem with the quadratic nonlinearities yet. So what do? Well, the first thing you do is normal forms. And this is another section of the talk where I have to apologize for people who know all about normal forms, as I'm going to explain the idea here. So essentially, well, suppose you have an equation in unknown theta, and it looks like quadratic plus cubic in higher order. That looks like this. And you write down the energy estimates, and you get something like this. And there's this bad term that looks third order that you'd like not to be there in order to make everything work. So the idea is that you perturb your unknown a little bit by a bilinear form. And you do it in this way or this way plus cubic terms, which is all right. And when you plug everything in, this is engineered to exactly cancel the quadratic terms. So that's sort of the idea. And you can just write down what this thing is explicitly. It builds in a little bit of loss of regularity, so you have to do some work to make sure that these quadratic terms you're accounting for are written in a nice way to avoid loss of regularity. And the other problem is you have to always be aware of these, these resonance problems. If you write this thing in Fourier space, you may get singularities around certain wave numbers, and this is bad. So you need to make sure those either aren't there or write in such a way that they aren't. And it turns out this is not a problem. You can always have the nonlinearities written in such a way that the derivative loss is not too big a deal. And it turns out that this special null form structure in the quadratic nonlinearities is just exactly what you need in order to kill the singularities coming in the denominator of this thing. So it sort of kills all the resonances. So this is, I guess, if you can't get rid of all the quadratic nonlinearities, CGWA's change of variables at least makes it so that you can use normal forms relatively easily. That's kind of the story. There is one annoying detail that comes up, which is that you use normal forms on things that look like this, and not all the quadratic nonlinearities present terms like this. In the energy estimates, there's other things. And essentially, the way they come up is when you do the energy estimates, time derivatives land in the wrong places. So the way that I thought to take care of this is to quote-unquote integrate by parts in time, which is not really what you're doing. What you're really doing is you're adding third-order energy corrections to the energy. When you do that, it's as though if you had a term like this in your energy estimate, you could, at the expense of putting something like this in the energy, which is lower order, or higher, it's smaller anyway, you could kind of put the time derivatives in other places. And so what you have to do is you have to add a really, really carefully constructed third-order correction that kills these quadratic nonlinearities that are in the wrong form. And by doing that, you either get ones that are in the right form, or you just cancel them off entirely. You can just sweep the rest up by using more normal forms. And here's the big theorem. What do I want to mention here? Really, the only sort of quantitative difference here is I've got a bigger remainder because I did more work to develop the approximate solution. And I have to assume this algebraic decay a little bit. So I have to assume it decays like x to the minus delta in the first 3 derivatives, I guess. Everything else is the same as in 2D. Okay.
May I ask a naive question?
Sure.
About, well, I'm not sure how naive it would be. In my mind, when I compare the two approaches, yours with Guido's, I have that, so talking 2D, Guido's kind of using classical normal forms, and the problem he's fighting with is the loss of derivatives. So he's using an analytic spaces with ever smaller domains of analyticity to overcome this. But you've got this change of variables which gets rid of the quadratic terms to avoid this problem kind of altogether.
It avoids it completely, yeah, exactly, that's right.
Now in 3D though, you've got this change of variables which gets rid of some of the quadratic terms, and you still have to do kind of classical normal forms afterwards as well.
That's right.
So this issue of loss in derivatives must be affecting you somehow as well at this stage.
Well, so if you were to try to jump right to classical normal forms directly, you would run into quadratic terms for which you have resonances that you can do nothing about if you were to stay in Lagrangian coordinates. So somehow using Cj's coordinates gets rid of all the really bad resonant quadratic nonlinearities. The ones that are left are treatable by normal forms. That's pretty much what it comes down to, I guess, yeah.
So where did you use the Clifford analysis?
Everywhere. Oh, Clifford now, oh man.
So is the key actually the generalization of the Hilbert transform, or is there more to it?
Yeah, ultimately what it comes down to is you need to write down her change of variables. In order to do that, you need a Hilbert transform. So it's just literally, it's very close to just following what you do in 2D, except you're doing everything in this Clifford framework.
Okay, so I'm not that familiar with this, so if you could kind of give me a basic idea. The Hilbert transform we normally think of is exchanging the real and imaginary parts on the boundary.
It is, yeah, it's very similar. So in this case, instead of the real
What do you
imaginary parts, if you think about like a 2D surface, it would be exchanging the tangential and normal components.
So it's not like a quaternion where you have 4 components.
Yeah, so there's always this very annoying scalar component. And it turns out that in the full water rate problem, the structure of the equations is such that the real component never shows up, essentially. Now, when you construct the approximate solutions, these scalar parts show up in the remainder, but they end up being very, very, very small.
So what, are they physical coordinates, the 3?
Yeah, the three coordinates are spatial coordinates, yeah. X, Y, Z.
The
Oh, yeah.
formulation.
Yeah.
Okay.
Yep. And you've got this extra coordinate running around that you just sort of don't think about.
That's interesting. Is it possible that it might actually be useful? I mean, sometimes when we sweep things under the carpet, we find out later they're interesting.
I mean, if you take this, this is actually, I guess, apparently how Maxwell wrote down Maxwell's equations. They started out with quaternions and looked at the vector and scalar parts, and that ends up corresponding for the vector operations to like div and curl. So if you wanted, I guess you could take Cj's quaternion approach and split up into scalar and vector parts, if you like. But yeah, the quaternion approach is very compact, so I sort of found no utility in bringing it up.
Thank you.